Okay, so thanks a lot, Renzo, for having me here. And it's a pleasure to give a talk. And this talk actually, in fact, continues with the previous one quite a lot, even with some observations that I made upstairs an hour ago. Basically, my goal here, let me tell you what my motivation here is for this goal is that we have studied Eulerian Kirschofian vortices quite extensively. The unpleasant point for me there is that the short distance behavior is logarithmically divergent. We have to introduce delta functions. So my motivation for this work originally was, how can I find a representation of those vortices in a natural fashion so that I can talk about finite energies and never encounter any kind of a cutoff need for introducing a cutoff for short distances. And for that, I introduced a field theoretical description of flight dynamical vortices. So this is oh wow, this goes really strange. I think I have some problems here with the screen because I'm supposed to have this neatly placed one after another, but they seem to be going up and down here and there. In any case, my collaborators are Anton Alexeev, Jin Dai, and Julian Karaut and Frank Wilczek at different stages of this work. So this was, how did I say it? Oh, if I could only use my own computer. Okay, so these are shortly the 4 points that I will discuss. I will first give you a short description of vortices, basically at the textbook level, how they appear in the Gross-Pitaevskii equation in a harmonic trap. Then I will tell you about vortices and the concept of time crystals and why I think that these are very nice realizations of time crystals in Hamiltonian contents. I will then show that the vortices in the Gross-Pitaevskii model are actually anions. All this is in a two-dimensional content, and the challenge would be to raise this in a one higher dimension. But let's see, that's for future. And finally, I talk about the saddle points that we know, if we think about it, had to be there, but haven't really been analyzed. And so using the Poincaré index formula, not the Poincaré-Hopf index theorem, but the refinement of it, how they can be neatly analyzed in the context that I discussed. So I start with the Gross-Pitaevskii, and this is really a textbook level standard results that are about 20 years old or so. So we are interested in basically the nonlinear Schrödinger equation in a harmonic trap. The first terms here are just the equation, harmonic oscillator equation, to which we add the cubic nonlinearity at the level of the equations. And we are looking for solutions to this equation. You can introduce here for the complex field, you can introduce Madelung transformations, you can introduce Hashimoto variables, and you can get it connected to fluid dynamical systems, to strings, Frenet equations, also as you wish, whatever is your favorite scenario. The equation is the same, and basically this is the analysis of this equation. And the free energy here is the Gross-Pitaevskii free energy. It will be always finite in my studies, and I'm interested in its minimizations in a way. And there are a lot of rigorous results that have been derived, in particular by Elliot Leib and his collaborators in both two-dimensional and three-dimensional content. And maybe the most relevant point that Leib proved is that in the limit of an infinitely many alkali atoms, this equation rigorously describes the ground state of the many-body Hamiltonian that describes n alkali atoms in a harmonic trap. For something like 10 to 4, 10 to 6 alkali atoms, which is a typical experimental scenario, if you look at the parameters, I have rescaled variables here and redefined fields from the physically derived version. But typically here, if you take the coupling constant to be between 5 and 500, you can describe this kind of experimental situations. So the Hamiltonian aspects of this, I use Hamiltonian formalism, so to say. The Hamiltonian aspect is that if you look at this action from which you get the equation by variation, then this action dictates that psi and psi star are canonically conjugate variables. So you have a Poisson brackets there, and you find out that there are exactly two conserved quantities that commute with the Hamiltonian when you compute the Poisson brackets. These are the number of particles that I normalize to 1 always, and the angular momentum, the z component of the three-dimensional angular momentum, that is also a conserved quantity. Note that this three-dimensional angular momentum is here really, all this is macroscopic. I'm talking about the wave function that describes large number of particles. And I have normalized the number of particles to be 1. Even if all the individual atoms have angular momentum that is quantized, I can take this angular momentum that appears here as have a continuous values. Corrections are 1 over n. So it is basically its values are not quantized and can have any real value, so to say, in the limit of large number of fields. In addition of these two conserved quantities, one also characterizes the structures here using the vorticity, that is line integrals of the argument of the phase, gradient of the phase, as both that has appeared already a couple of times in this talk today. So the results that were derived during the last 20 years around is that the basic results, and this is the where things stood when we got interested in this problem. Basically, clearly there are no solutions to the classical static equation of motion. If you look for the critical points of the free energy, there are no solutions because it's a sum of 3 positive terms. So in order to get stable solutions here, you have to take your container, the gas, and start to rotate it. You rotate it with the angular velocity omega, then that amounts to time-dependent coordinate transformation, and at the level of the field, it is generated by Poisson bracket with the angular momentum. If I substitute this, that is, I take the classical action and I go into take the free energy and I go to co-rotating frame. Then I find out that the free energy has this form where I have introduced now a chemical potential that is conjugate to the particle number. And I also have the angular velocity that describes the angular speed, how I rotate the system rotates. And then one can show that when I add these two terms, or basically this term, into the free energy and I look for the variational equation of this functional, then this functional can have finite energy solutions. If omega is sufficiently large. That is, I have basically an eigenvalue equation here, nonlinear Schrödinger equation, eigenvalue equation for the chemical potential. And these solutions have been found both theoretically and experimentally, and the match between theory and experiment is fabulous. Theoretically, one finds that when omega increases, when omega is very small, we don't have any soliton. We just have basically a uniform distribution. Now, this uniform distribution comes there because I have fixed the particle number to be 1. I have basically a normalizable wave function, ground state of a harmonic oscillator. When I increase the omega, so for small values of omega, if I look for the energy diagram for some typical parameter coupling constant here, for small values of omega, I have no vortices. The one vortex solution is unstable, but there is a critical value of omega where the one vortex solution has a lower energy than the original wave function, And then that describes the lowest energy configuration in this particular system. When I increase the value of omega, rotate it faster, there is two vortex solution becomes stable, then a three vortex solutions and so on. I find out a series of vortex solutions from 0 vortices, 1, 2, 3, 4, 5, and so on, that emerge when I start to rotate the system faster and faster. And they form very nice Abrikosov lattices. The details of the geometric structure depends then on the coupling constant G. And experimentally, when one does the same in some alkali atoms, one finds, I had to blame Renzo that it's so warm here that I get thirsty. So I find the same, experimentally one finds exactly similar kind of phenomena that one finds theoretically. But here one point is that in the case of Euler equation, where we usually talk about vortices and their interactions by how they move by localized induction approximation and so on, where we encounter always logarithmic divergences that we have to cut off. Here, there is no need for cutoff. The energies are always finite. The cutoff is provided by the theory itself because it's not a point vortex theory, it's a field theoretical vortices. If I take the limit here, I can take a limit where I recover the point like Euler vortices by going into the, so to say, London limit, where I let the density go more and more confined in the constant value. So this is what is known about the Gross-Pitaevskii equation. So let me now go beyond the Gross-Pitaevskii equation and show that there is actually more. This is what was supposed to be full analysis of the situation, but there is actually more. And let me now first introduce the concept of time crystal. Time crystal is a kind of a concept that was introduced by Frank Wilczek 10 years ago. And initially it was ridiculed. Frank says, I've never been ridiculed that much. But now slowly it turns out that actually this kind of a solutions or systems do arise. Well, the Wikipedia has a paradigm there. They actually changed this now when I took it. So this is the way it said is that time crystal it's a dynamic, it's a physical system that can never reach an equilibrium. It can only move. The ground state, the lowest energy state, would never be time independent stationary. It would always have to move. And one thought that this kind of systems can only exist in open systems that are driven systems. Why do we not expect time crystals to appear in a Hamiltonian systems? The simple argument is here is that if I look for Hamiltonian equations, the Hamiltonian equations say that if I'm looking for time dependent systems, P dot and Q dot should be, at least one of them should be non-vanishing. But P dot is a gradient of H with respect to Q. Q dot is a gradient of H with respect to P with a minus sign. So if I want the configuration to be a minimum energy configuration, a minimum energy should be usually it's a critical point of the cost function, and consequently the right-hand side, the derivatives of H vanish, and P dot and Q dot also has to vanish. So clearly, if I want to have a Hamiltonian system where its minimum energy, and I'm interested in its minimum energy configuration, the minimum energy configuration always has to be time dependent, time independent. You cannot have time independent minimum energy configurations. But it's easy to find counterexample. I don't claim that this is a physical counterexample. It's just a little exercise what you can do. Suppose that I would have just a harmonic oscillator. And suppose that for some reason, maybe there's some physical reason, the P's and Q's would be subject to condition, that P plus Q is 1. Then if I look for the critical point of the H, the critical point is at the origin, but that would not be a minimum of this Hamiltonian, provided the Hamiltonian satisfies this condition. The minimum of the Hamiltonian, provided it satisfies this condition, occurs when P and Q are half. And in fact, if I use Hamiltonian equations to follow the time evolution here, if I use this Hamiltonian here and restrict myself to this condition, all the solutions would be time dependent because the gradient of H with this condition is always non-vanishing. So we had to then read carefully to go forward with this in a reasonable physical situation. We had to read for Lagrange multiplier theorem. Lagrange multiplier theorem, well, it's usually gone very quickly in at least the canonical theoretical physics goes, but economists use it more extensively because they want to minimize cost or maximize profit. And they have a lot of conditions. I took the formulation of the Lagrange multiplier theorem here from some economy book, optimization book. If you want to look a more elegant version, go and look for Marsden's textbook. This is of course something that he writes a lot about. But Lagrange multiplier theorem basically says that if I want to find a critical point, a minimum or maximum, here it's an economist, so minimum of minus f. If I want to find a minimum of minus f that is subject to some conditions G, I can find the minimum of f by looking for solution for Lagrange multiplier so that the critical point of f plus lambda G is 0. That is the gradient of f equals lambda times the gradient of G. Then I have the minimum or maximum of f is a critical point of this f plus lambda G, and I have enough equations there usually to solve not only for the critical point, but also the Lagrange multipliers. And once I have solved this, I have a solution of the problems how to minimize or maximize f subject to the condition G. So let me here. This is really annoying. I mean, now it's completely messed up my screen. This is what I worried. Let's see how we can make it's just getting worse. I'm sorry, but we can handle it. Okay, so we have to. Is there any way, sorry, to change the resolution here? Because now this is really messing up the resolution. I should have a clean distinction here where I have critical point and constraint optimization. So okay, but I can talk myself through here. If I'm interested in a standard way, that is in a very naive way of trying to asking the question is that I have a Hamiltonian system, and I want to find out the way how the minimum energy configuration of this Hamiltonian system goes. You know, people who want to go very quickly, they would take the derivative of the Hamiltonian. And it says, okay, it's a critical point, it got to be minimum, one of the critical points, if there are several, got to be a minimum. So if I look for the equation of motion, the minimum energy solution has to be time independent, nothing interesting happens there. But really if I have a system where I have a Hamiltonian H, and it is subject to the where did that disappear? Oh, conditions. Okay, it jumped up here. So there it goes up here. If it's subject to conditions, see, I mean, Microsoft and Apple, they really don't find a way to collaborate. So if you have I want to find a minimum of H subject to some conditions. That Lagrange multiplier theorem tells me I should look for H plus lambda G, where the lambda are the Lagrange multiplier. I should look for the critical point of f, H plus lambda G. That gives me these equations. Set of equations. From this set of equations, I can solve. I have enough equations, so in principle, I can at least locally, I can solve for the critical values of P, Q, and the Lagrange multipliers. And then, because the gradient of H is equal to the gradient of P multiplied by some lambda, I find out that the Hamiltonian equations, because I have a gradient here, I can replace the gradients by the gradients of the G, that is Poisson brackets of the G, and I find out the Hamiltonian flow would be given for the minimum energy configuration would be given by this set of equations. Usually these G's are symmetries, and that is the interesting case. And in that case, I would conclude that the minimum energy configuration is time dependent if the Lagrange multipliers are non-vanishing, and the ground state configuration would be a symmetry transformation, but it would be time dependent. So basically, the time crystal in that case is where G is a symmetry. That is often the case. The time crystals would just be a time minimum energy configuration that minimizes the Hamiltonian, and it defines a symmetry transformation of the system. So okay, I don't have any major problems here. Everything seems to be okay. So then the question that we can have is, are there, I showed that the Gross-Pitaevskii equation, if I rotate it uniformly, it has only very symmetric, nice Abrikosov lattice vortices. Now the question is that suppose that I don't rotate it, but I say that I'm interested in minimizing the Hamiltonian subject to the condition that there is a certain number of particles. I normalize it to the wave function so that I have one, n is 1. Remember, n and L are constant quantities. They commute with the Hamiltonian. But for L, the angular momentum, I say that the angular momentum has, I keep this some numerical value, small lz. And I'm interested in finding, can I find a minimum of this free energy subject to these conditions? And what are the properties of this condition? Let me point out here that this LC, it is not quantized. It can be basically, because I have in the limit of infinite number of particles, it is basically a continuous variable, and you can change it without rotating. There, for example, experimentalists tell me is that you can probe the system with the laser, polarized light, or so on, and that introduces angular momentum without any motion. Or you can use the Higgs-Kibble mechanism to go through some kind of a phase transition, and that can introduce, but it's so I can meaningfully ask a question of physically relevant way to ask for this kind of optimization problem. So I should look for critical points of this free energy here, that I have two Lagrange multipliers that I introduce. And if I just then write the equations, this is the set of equations that I need to solve, and I need to find out then that psi and those values of the Lagrange multipliers that give me a minimum of the original free energy function. So that is what I want to find. Okay, so let's go forward. So this is basically so then what I find is that, so you find if I find this lambda minima, because the gradient of the free energy is equal to the gradient of the symmetry transformations times the Lagrange multipliers, I just go to this equation. That is, I can write the equation, Hamiltonian equations in terms of the right-hand side here for the minimum energy configuration. So the minimum energy configurations would then solve an equation, would then give me a solution like this. It would give me a time-dependent, provided the Lagrange multipliers are time-dependent, it would give me a time-dependent solution, but the time-dependent solution is basically a symmetry transformation with respect to the gradients of the number operator and the angular momentum in a certain combination. They are both generator of U1 in this case, so I have a U1 cross U1 symmetry broken down into U1, diagonal U1, and the minimum energy configuration would be time-dependent, basically a symmetry transformation with this U1. Well, we have done, this is not the easy task to solve, it is, goes into heavy numerics, and Julian Caround has basically, my collaborator, who seems to be quite top on this, has done the numerical simulations. And this is what we find. Here, okay, so the movie goes on. Here I show what we find out. Okay, so what I I will show you now is that I will show you the solution, the minimum energy solution that we get, starting from L is 0. If L is 0, of course, it's just a harmonic oscillator ground state wave function. And then I will proceed with the L. Here is the density, and here is the phase. Here I display the phase, and here I display the density with the. This should now. Okay, probably. Okay, now it starts. So here you see how all this rotates then uniformly by lambda. This is in a co-moving frame that I have written here. You see that there is a one vortex solution that is not initially diagonal. It appears from the boundary, and then a two vortex solution comes. They are asymmetric. That is, they are different vortices, so to say. Then they form a pair. A third vortex starts to come, and the phases go accordingly. So you see here in particular, let's go to the next page. You see here that the spectrum is very different from the spectrum in the case of a conventional approach to the Gross-Pitaevskii equation, where one only minimizes the free energy in a rotating frame, because there the one vortex solution could only exist after a certain critical value of the rotation, and it appeared at the center of the trap. The two vortex solution was, so basically it would be like this. That kind of a solutions would not exist there, nor would this kind of solutions where you have one vortex in the center of the trap and the second one appearing. Here the two are symmetrically, they start to form a lattice, and the third vertex goes on. Here I have results, the spectrum for three different values of the coupling constant. You see that, for example, if I use a coupling constant 5, so the minimum values of the lambdas are non-vanishing. If the solutions for the lambdas are non-vanishing, the system moves because it is a symmetry transformation of the rate of the lambdas. There are no coupling constant, the Lagrange multipliers never go to 0. So all these are time-dependent solutions, one way or another. Here I find that if I show the coupling constant 5, so it goes the Lagrange multipliers change. Then I come to the point. This is a point. It is kind of a jump where the vortex gets on the center of the trap, and the second vortex then that is where the first vortex goes to the center, then second vortex appears, and you see that this dots here are symmetric configuration. It is symmetric when there is only one vortex because it's sitting there. Then the two vortex solution is symmetric and approaches 10 or 3 vortex solutions and so on. So you see a very nice systematic behavior here. And in the case of the conventional approach, you would only see this solution. Here you would see nothing. You would see this solution, you would see this solution, and so on. So these are now clearly solutions to the Hamiltonian time evolution of the minimum energy of the Gross-Pitaevskii functional that describes a given number of particles and that move with a given angular momentum. Since this is a minimum energy configuration in a Hamiltonian system, in that sense it qualifies as a time crystal. That is, the minimum energy configuration always moves, even if it's a minimum of Hamiltonian. So now let me point out something quite curious here, is that I don't know if you have heard about anions. Anions, here is kind of a very simple description for this, is that anions are two-dimensional particles. In fact, they exist also in 3 dimensions. With Paul, we had this leapfrogging smoke rings, and we kind of made a point that they are generalization of this, so they are kind of anionic in 3 dimensions. But in 2 dimensions, you can have either bosons. If you exchange 2 bosons, the wave function doesn't change. If you have a fermion, if you exchange them, the wave function changes by -1. But if you have an anion and you exchange them, the wave function can change by anything. That's why they are called anyons. So let's see what happens, because we had the solution. So let's see what happens if I take one vortex solution and two vortex solutions. And you can take one vortex solution and then you can just look for its time evolution, where you use these Lagrange multipliers that I have solved by the minimization problem. Then I can take and see how the phase evolves. Then I don't dare to code them now because I don't know how this reacts. So I go a little first explain and then we'll see the movies. Here I have then a two vortex solution, a symmetric two vortex solution. So it describes two identical, a priori identical particles, but then I exchange them and we can see here we see how the exchange proceeds. And I follow the time evolution, and here you can see how the phase forms, and you can see that the phase doesn't go by n pi when I make a full rotation. So this is what happens. Okay, the one solution, you see that if it when rotates the trap center, it changes like that, and the two vortex solution then changes their phase evolution is not a multiple of so in this sense, the vortices that the vortex solutions that we have them when we exchange them, their exchange statistics is anionic. So here I actually show you what goes on if I analyze this anionic structure a little more. So let me start from this equation that is the original Hamiltonian equation, where I look for the minimum energy configuration and I replace the gradients of the Hamiltonian by the Lagrange multipliers times the gradients of the conserved quantities. The equation has this form, but I can directly write it the right-hand side into this form. That is, I have some parameter here. I take the z component of the angular momentum. This is the angular momentum, but it is not the normal kinetic angular momentum that appears that you have there, but it is shifted by a gauge field. It is shifted by a gauge field with this that Renzo already once pointed out here, with a statistical factor that is the ratio of these Lagrange multipliers. So it is the ratio of these Lagrange multipliers. If it's not an integer, as it usually is not, I mean, we had here a spectrum, we look for the values here. They are not integer, they are quite general. So for general value of the ratio of the parameters, the effective statistical coupling there, statistical weight is a non-integer, and this is the standard form of evolution equation for anions on a two-dimensional plane. So that is what you find here. So let's go forward. And let me point out that actually I think I had a contact. I haven't contacted these experimenters yet. There was a paper by Wieman and Cornell. Those are the two Nobel Prize winners who first constructed vortices and constructed Bose-Einstein condensates. They had a nice paper 22 years ago where they found that they can have an off-diagonal vortex in a certain situation, and this off-diagonal vortex seems to rotate around the trap center. So it looks very similar to the phenomena that we have found here, but not any attention basically has been put to this from theoretical point of view. But if this result here stands, it could be that the anions were found already 22 years ago and not 2 years ago, like now it appears to be the case. Okay, so there's something more that one can dig out here, that we know if we know about vector fields in a plane, we know that it has to be there. We don't usually discuss that when we think about point vortices. We don't even discuss that too much when we, well, I haven't seen any discussion, in fact, when talk about field theoretical vortices, and that's the saddle points. and what I will go and explain now. They have any nice phenomenology dynamics associated to them. So conventionally, when we talk about superfluid vortices, so we have this psi. If you want to talk about fluid dynamical, do your Madelung transformation there. This is not detailed, but the details of the model. We can have two kind of vortices. We can have vortices where the vector field, the gradient of the phase, circulates in the clockwise direction around the vortex center, and anti-vortex where it rotates counterclockwise around the vortex center. So these are vortices, anti-vortices, and we usually detect them by computing this circulation that has already been discussed in here. And normally we do not associate any other topological invariance on a problem where we look for this wave function. But if you think about, I'm sure that you figure yes, of course, but because if you think about it, you do see that there are also additional points, and let's enumerate them. If I have one vortex in my trap, okay, I can just see that there's one vortex. But if I have two vortices just don't appear like that. If I have two vortices and I look for the velocity field, I find also that there's a point, stagnation point, or a saddle point that appears. This saddle point appears typically in this kind of situation. It likes to be there in these numerical simulations. It likes to be there between these two vortices. And if then eventually, when I go to a situation where the two vortices form the symmetric configuration around the trap center, these two saddle points aggregate at the center of the trap. If I then have three vortices, I see that they also again try to aggregate. They try to aggregate to the center of the trap. So what I find when I look for this, not only the vortices and their Abrikosov lattices, but I also look for the geometry of the saddle points. The saddle points aggregate at the center of the lattice. And I couldn't, you will see even more impressive picture. When I saw this picture, I couldn't get my eyes off this photo that you see upstairs of vortices and aggregation at the center, whatever this. It was just a visual wow, the same. But then something interesting happens. When we increase the number of vortices, this depends on the coupling constant. And when I increase the angular momentum, that is, I increase the number of the vortices, they continue to aggregate. It starts to look more and more like the picture upstairs, with vortices arranged around the aggregation of saddle points. But then what happens there is an interesting transition that I haven't fully analyzed or gone into the depth of it. But what I find is that if I increase the number of vortices, I find out that the saddle points don't all aggregate anymore. Here I see that one of the saddle points actually likes to be close to the vortex. When I increase it further, I see a clear transition. Here between 4.1 and 4.7, these values, I see no aggregation anymore. Now I see just vortex saddle pairs forming. And this seems to be the pattern. The higher the angular momentum, all this depends, of course, numerics here is just a representative. The more there are saddle points, but the saddle points and vortices tend to aggregate more and more around in the pairs. This is actually something which is very similar to the Kosterlitz-Stauss transition that you mentioned, the work of Kosterlitz-Stauss. They considered the XY spin model. Basically, they considered the very similar model that I consider here. They took the wave function and they defined a vector from the wave function. They took the two-dimensional vector, that is where the x component is the cosine of the argument of the wave function, and the y is the sine of the argument of the wave function. And in the XY model, they speculated, they introduced this, they observed this Kosterlitz-Stauss phase transition, that when they look for vortices in this picture, the vortices for small beta, that is a large temperature, the vortices and anti-vortices were completely randomly distributed there. That is, they were not paired at all. It was maybe a little like this kind of an aggregation, they tried to aggregate, but large p, that is small temperature, they started to form vortex-anti-vortex pair. And this is something that was then is called the Kosterlitz-Towles phase transition. It is one can show that these two extremes are two different phases. The transition between the phases is not so well understood. One can look rigorously, I think Fröhlich and Lieb and so they have looked this rigorously and proven rigorously that there are different phases, but this phase transition is not so sharp as often it's found. Let me point out here is that if I go to London limit, that is limit where the density is constant. This is where I get the Euler-Kirchhoff vortices. In that limit, these vortices have a logarithmic divergence in their self-energy if I strictly go to London limit. But the saddle points here, they always have basically zero, very small self-energy. So if I now analyze this, let me, the rest of this is kind of explaining maybe some, what I find at least confusing in the literature. If you look at this Kosterlitz, if you look at the Kosterlitz-Towles description of vortices and anti-vortices. So in Kosterlitz-Towles language, vortices are centers and anti-vortices are saddles. This you can easily see when vortices and anti-vortices go together, they annihilate each other topologically, and that is what they viewed vortices and anti-vortices. Now this motivates actually that we introduce two topological quantities to describe vector fields on a plane, even we analyze this kind of physical scenarios. One is the standard circulation that we use always, for example, in the case of vortices normally, but we can also define a winding number. And these are two different topological invariants. You can see them that this circulation is odd in V, the winding number is even in V. And it turns out that this winding number actually has more power, so to say, to separate what are vortices, anti-vortices, and centers and saddles. Because if I just look for circulation, for a center that is a vortex, this integral is either +1 if the vector is oriented along the curve, or -1 if I go the other direction. While for a saddle, clearly it vanishes, because if you take a curve here, you see that there's a complete symmetry. It goes against, for, against, and in line, so it is 0. While the winding number separates, it's not able to separate the direction of the circulation here because it's even in V, but it detects centers, vortices by assigning them number 1 and saddles by assigning them number -1. So if I want to go into these more general structures by not only vortices but also stagnation points, this winding number has some advantage. And sure, there is an advantage, and this also relates nicely to index theorem. Different that the circulation, which is more like a same character. Here we have, I just advertised this because I haven't really seen this in particular index theorem discussed so much in the physics literature, at least. Usually it is one thinks that it's the same as the Poincaré-Hopf, but it's not the same as the Poincaré-Hopf. It's more refined. It's called the Poincaré index formula. And it says that if I want to study centers, vortices, if I want to study saddle points, or if I want to figure out, it's particularly useful if I have a messy situation like that, aggregation. How do I figure out how many, can I convince how many saddle points there are if it's so messy? Well, what I do is that I take any arbitrary trajectory. I can take any arbitrary trajectory there, and then I just count how many internal and external tangencies this vector field has for this arbitrary trajectory. And the number of internal and external tangencies, that gives me the number of the index, the net number of vortices, less the number of saddle points as the Euler character and half the number of internal and external tangencies. And that's the Poincaré index formula. If you exclude this, you get the Poincaré-Hopf index theorem. I just wanted to advertise it because it's not been so much present. And just this is more something that I should maybe tell my undergraduate students or so on. Just a little example, that funny thing that we observed when we try to figure out what's the difference between saddle points and vortices. If I look for the index, saddle points have a binding number -1, vortices have a binding number +1. If I now integrate the same direct, well, have an index +1. But what happens if, for example, one example of a vortex is that Vx, Vy is -Yx, while a saddle is Vx, Vy is Yx. But suppose that I now make just a rotation, coordinate transformation where I rotate coordinates by time dependently. So it is neat to see how the saddle stays a saddle. I mean, it's a saddle that rotates. But the vortex goes into attractive, repulsive, and then it changes its direction. So a vortex and anti-vortex are the same here. Vortex is just you go to rotate counterclockwise, and now you locate clockwise, and so on. So it is that's the way how they are topologically equivalent, and that is we know, of course, that they are all at their fixed points except the saddle has index +1 in the sense of binding number. That's basically something. So that's about all I wanted to say, and there are some lessons that I hope you can take from this talk. That usually when we look for physical systems, we want to look for minimum energy configurations, and we want to look those as a critical points because we want to then solve some equations. It turns out this is a too restricted point of view. You had to look for minimization problem more generally. And it is actually from a more general point of view, if you have conditions, usually the minimum, those configurations that minimize your energy in Hamiltonian contents, those are usually not critical points of the Hamiltonian, but you had to identify them more generally using the Lagrange multiplier theorem, and then you find out that those minimum energy configurations are actually time dependent. They are time crystals, and as I showed in many cases, the conditions are generators of symmetries. That is, they generate symmetries of the physical system, and as a consequence, the time evolution is a symmetric transformation of your theory. And there are new physical phenomena. That is, you have anionic. You can have anionic phase evolution, like I showed in the case of the two vortices. You can have there are time crystalline realizations of the time crystalline dynamics. You can have a kind of a Kostelis-Tauss transitions between from the aggregation of saddle points to the vortex saddle point pair formation. And they are nice. It is nice to little extend the arsenal of the index theorems in the two-dimensional case that we use here in addition of Poincaré-Hopf. It is nice to keep in mind the Poincaré index formula that treats that is more specific. Poincaré-Hopf always assumes that the vector field points to the exterior of the domain that you are interested in, and that's not the general case. But all this is 2 dimensions, and the challenge is how to do something along these lines in the 3 dimensions where these structures get highly knotty, so to say. Okay, that's all that I wanted to tell.